All right. I think we're here. Well, first of all, I'm going to ask the simple question. Can you guys hear me? If you can hear me, please send a message in the chat relay, which is the first five digits of pi. Okay, that way we'll know whether or not you answered yes to some random questions about cats or whether or not you are here. Oh, I guess someone said you can hear me. Oh, okay, sounds good, sounds good. All right. Well, I must say, it is such a great coincidence to be doing this live solve together with MathCounts on Pi Day. You see, we are absolutely thrilled to collaborate with MathCounts every year because MathCounts in the United States is actually I think it's the largest tournament style face-to-face math contest for middle school kids. And the beautiful thing is it's team-based. So that's what got me into math. I started out as a kid in Wisconsin. The next state over from Luke, actually. But so I was a kid in Wisconsin, and I didn't really know anything about what advanced math was. But somehow, because it was a team contest, people pulled me in as a sixth grader, and that changed my life. So because of math counts, I do what I do today. And then I just decided I wanted to help give back as well. And so every single year, we're very happy to do this live solve. I see some people already are doing things like raise hand. I want to tell you the way to operate in this system, send messages, not to me, not to Eli, not to Luke, but send them to chat relay. And then they're going to start to appear on the screen. If you're wondering how come your message didn't get through, it's because we don't want the whole thing to be total spam. And so only one message gets through every second. Unless your message is so interesting that our moderators say, "Doop," it goes through, then a star appears. That's what those stars are. Okay? If you say things that aren't super nice, unfortunately, the moderators will take them out. But something about the way this is, we want to first of all acknowledge the official collaboration here that we have with MathCounts. We, on this channel, are quite careful not to just put on random other people's contests without working with them. And so this is official collaboration. But of course, we're proud to do this because all of us are happy to support MathCounts. Now, if you're coming from outside the United States, you'll get a taste of what all these questions are. The way that we do these live solves is, unfortunately, I don't have the same cool equipment that our instructors have. You can already tell, because I'm in some boring hotel room actually outside of London. But at least it's better than the airport that I did the AMC8 live solve from. The way that we'll do this is that our two incredible instructors are going to be doing the questions, and I'll actually be here making a commentary about maybe any other idea that I have. Oftentimes they'll have a very good solution, but I mean, maybe even better than what I came up with. But I also want to say none of us looked at the questions beforehand. So that's the whole point. We actually want to show you how people think through these questions if they're looking at them for the first time. All right. Well, with that, I'm going to toss it over to Eli and Luke. Usually they introduce each other, but the first person to speak is the one with the alphabetical earlier. So Eli will be the first introducing Luke, and then vice versa. And then we'll dive into some questions for about an hour and a half. Eli, why don't you take it away?
Yeah, sounds good, Professor Loh. Okay, so I guess I should introduce the person to my right, Luke Furness. Luke is not only a AMC8 perfect scorer, he's also a four-time Amy qualifier and math counts. He represented Michigan at nationals. So there you go. Very qualified to do this live solve with us. And outside of math, he's also very into guitar. So everyone, please welcome Luke as my co-teacher for today.
Yeah. Hi, everybody. I'm so excited to be going today, and it's just going to be a great live solve in general. And Eli is also a really cool person. Eli is a student at Princeton University studying math and music with a minor in Chinese language. He is a U.S. presidential scholar and a two-time USA Mathematical Talent Search perfect scorer, which is amazing. Outside of live, he teaches for the Cambridge Math Circle and is trying to start his own math circle in New Jersey. He's also a world-class percussionist and marimba specialist, and he's been featured by the U.S. Navy Band and won countless competitions. He loves combining math and music by practicing the English folk tradition of change ringing, which involves ringing mathematical permutations of ring-tuned bells, which sounds very interesting.
Yeah, and
Challenge.
Professor Lowe, I feel like may have even heard change ringing in London. Maybe, I don't know. But it's very common in England. So yeah.
All right. So that does it for the introductions, and now I think we're just gonna hop straight into the problems. So we're gonna be doing all the problems from the sprint round tonight, 1 through 30. So we're gonna start off with problem 1. And Eli, do you want to take this one?
Yeah, sure. Okay, so looks pretty straightforward off the bat. Just a computational question. What's the value of 7 times 2 minus 3 times 4 plus 2? Okay, this is 14. 3 times 4 is 12 plus 2 is also 14. So I'm getting 0. I'm going to assume that this is right. So It is. Yay. Cool. I don't think there's much to say here. Luke, you can
Yeah,
take the next one.
yeah. As you guys know, the problems will get harder, so don't worry. You will be challenged at some point. All right, problem 2. Stephanie went to the store to buy chocolates for each of her 5 classmates. To buy 3 chocolates for each of her classmates. While shopping, she decided to buy 5 chocolates for each classmate. How many additional pieces does she need to buy compared to her original plan? So her original plan is to buy 3 chocolates per person. So we have 5 people, and we're buying 3 chocolates per person. So that means that we're going to have a total of 15 chocolates that she buys. And then in the second plan, we're going to buy 5 chocolates per person. So 5 people, and then 5 chocolates per person. So we're buying 25 in the other plan. So the original plan was 15. The second plan is 25. So 25 minus 15, we bought 10 additional chocolates in our other plan. So 10 should be the answer for question number 2. And hopefully I did not get this one wrong as well. Yes, the answer is number 10. All right, back to Eli for the next one.
All right. Question number 3. What is the least perfect square whose digits are all prime? Okay. I feel like there's nothing interesting here. I'm just going to like start listing the perfect squares. And I can just think 25 is the answer. I mean, I just went through it. 1, 4, 9, 16. These all don't work because they all have things that are not prime, but then 25 works because 2 and 5 are prime. So I'm just going to say 25 and I'm just be done with it. Yeah, looks right. Okay, cool. Next question.
Good job. I love how you just like immediately knew. You just saw the question, you're like, oh, the answer is 25. I already know. That's insane. Okay, moving on to the next question. Triangle ABC shown is a right triangle with side length AC extended. What is the value of x plus y? Okay, so the key idea here is that the 3 angles of a triangle are going to add up to 180, right? This is true of all triangles, just something you learn in geometry. So this right angle here is going to be very important for us. We have a right angle at BAC. So that means that we have a 90-degree angle right here, and then we have a 60-degree angle right here. So because those 3 angles are going to add up to 180, we know that 60 plus 90 plus y is going to equal 180. So this is equal to 150. So y is going to be equal to 30 right here. 30. So 30 is the angle right here. And then over here, we know that x plus 60 is going to equal 180 because these 2 angles make up a line like here. And the angles that make up a line, so like this angle right here will be 180. So x plus 60 is equal to 180. So x is equal to 120. So now we have to add 120 and 30 together, and we get 150 as our final answer. So hopefully that's correct. And yes, the answer is 150. All right, back to Eli for the
Ooh,
next one.
I just want to jump in because I saw someone raise a hand. I just want to say the way to respond and interact here, send messages to chat relay because unfortunately we won't be calling on people for a simple reason that we actually are putting this also on YouTube. So we want to protect people's privacy and all that. So interact with the chat, please. But back to you.
Yeah, absolutely. Okay, so question number 5 on the speed round. How many lines of symmetry of a regular octagon go through at least one of its vertices? Okay, so I think we just have to like look at all of the lines of symmetry that pass through a vertex. Certainly, it can't pass through only one and then just not pass through another, because then it would not be symmetric. I think the only lines that you get are things like this. You can even just draw all of them. Imagine they went through the vertices, and it looks like there's 4. I mean, I think it's just 8 divided by 2 because there's 8 vertices, and every line goes through 2 of them. So yeah, I'm pretty confident in 4. I don't think there's anything else going on here. So yeah, 4 seems to be the right answer.
I want to say when I saw that, I got scared because it feels like it's supposed to be sneakier or harder. But good, Eli, you were right. It's good.
Yeah,
Yeah,
I mean, I think in general, an octagon only has 8 lines of symmetry, right? So, the other 4 are just the ones that pass through like this, and these don't pass through a vertex. So you can just get rid of those. Yeah, so I guess maybe if you didn't know that an octagon had these lines of symmetry and you try to like, oh, how do I prove that these are the only ones? Then maybe it's harder, but I'm not really caring about that. So yeah, I'm just gonna say the answer is 4 and be happy.
Yeah,
So, okay.
I agree. It definitely feels like you could miss one of the lines once you find your first four. You'd be like, oh, maybe there's more, but there aren't. So 4. Great job, Eli. Moving on now to problem 6. And now this is a very common type of math counts problem where they put in symbols that you have no idea what they mean. And I have never seen this symbol before, but we're going to have to work with it in this problem. So if x hashtag y is equal to 2x plus 3y, then 4 hashtag 1 is going to be equal to 11 because you plug in each of the x and the y into the equation. So what is 2 hashtag 3? 2 hashtag 3. So this is going to be equal to 2 times this first number right here, which corresponds to the first number we put here, plus 3 times the second number when we did the hashtag thing. So that's going to be the second number over here. So this is going to be equal to 2 times 2, because the 2 is the 2 right here, and that's the x in this original thing up here, plus 3 times y, or 3 in this case, because this 3 right here corresponds to the y that's up here. So 2 times 2 plus 3 times 3 is going to be equal to 13. And checking our answer, indeed the answer is 13. So yes.
Yes, lucky 13. I mean, it was so cool that yesterday was Friday the 13th and last month was Friday the 13th. This is like only possible when Friday the 13th happens in February and it's not a leap year. So that was pretty cool. But now it's the 14th, so we get to celebrate a different holiday, which is Pi Day. But it's also a Pi Day that happened right after Friday the 13th. So it's like kind of special in a lot of ways. Anyway, here we go. Next question seems to be some geometry. We have a rectangle. That's twice the area of the square with side length 8 centimeters. If one of the side lengths is 4, what's the perimeter? Okay, so we just have to find the area of this. That would be 64, right? It's 8 times 8. And we know that the area of this is exactly twice the area of this. Okay, so 4 times whatever that length is, 4 times x is double 64. So 2 times 64. Dividing by 4, okay, well, 2 times to be 16. 64 divided by 4 is 16. 2 times 16 is 32. So x seems to be 32. And we want the perimeter. So let's see if I can do this in my head. Let's be 4 plus 4 is 8, plus 32 is 40, plus 32 is 72. So I believe that should be our answer. Let's see if it's right. Yeah, it is. Okay, back to you.
Oh, cool. I just wanted to jump in. I wanted to say an idea to also add here, just because I'll occasionally throw in some thoughts. An idea to add here is that if the area doubles, somehow the 4 is half of the 8. So if one side goes half, maybe you can, there's another way that you can quickly see, double check or like that.
Yeah, so I mean, if one side is halved and the area doubles, then the other side needs to be quadrupled, right? So like here, in order to preserve the same area, I would have had to multiply this by 2, but in order to double it, I'd have to multiply it by another 2. And so I could just take the 8 and multiply it by 4. That also works. And we get the same answer of 32 there, and then we compute 72 again. All right.
Alrighty. Moving on to problem 8 now. Problem 8 says, Janelle writes the positive integers less than or equal to 26 on a whiteboard. What is the sum of the multiples of 3 that she wrote? So let's just write out all the multiples of 3 that we have and see if we can find a nice way to sum up all of them. So we have 3 plus 6 plus 9 plus 12 plus 15 plus 18 plus 21 plus 24. All right, so when you have a really long list of numbers like this, there's a really nice thing you can do. You can say, let's find the average of all these numbers, and then multiply that by the total number of numbers that we have. Because if you think about it, the average times the number of numbers will equal the sum of all of those numbers because of the definition of the word average, really. So in order to find the average, what we're going to do here is we're going to add up 3 and 24. So notice that when we add these up, this is the same. We're going to get the same sum as when we add up 6 and 21, 9 and 18, or 12 and 15. Those are all going to be the same sum, and it's all going to be 27. So you can find a bunch of pairs that add up to 27. So 27 divided by 2 is going to be our average, because for every 2 numbers, we can find 2 numbers that add up to 27. So 27 divided by 2, those 2 numbers add up to 27. So 27 divided by 2 is going to be our average, multiplied by a total of 8 numbers here. So 8 numbers times 27 is going to be equal to 108, which is our final answer. And one other way you could approach this problem is once you pair up all of these numbers, instead of finding the average, you could just say each of these pairs of numbers is equal to 27, and there's 4 of those pairs, so you could just do 27 times 4 just from there. But either way works really well, and we get 108 both ways. And yes, that is our answer.
All right, yes, 108. I don't know why I really like the number 108 because it's divisible by 18. And I don't know, it's just cool. Like you can add as many zeros as you want and it's always going to be divisible by 18. And I just find that fun. I know that it's like obvious from certain divisibility perspectives, but like it's just a nice multiple of 18, 100, whatever. Okay, question number 9. A right triangle has side lengths 7 halves, 29/6, and 10/3 inches. That's great. Okay, what is its area? Express your answer as a common fraction. So I guess the point of this is to try to figure out which one's the hypotenuse. So really all we have to do is figure out which of these fractions is the biggest. I mean, I think we can just do this. Like this, the first one is 3.5, that's 7 halves, 29/6. Let's see, that would be 30. So like a little bit less than 5, right? So like 5 minus, I'll just write it as 5 minus a sixth. And the last one is like 3.3 repeating-ish. I mean, clearly this is the winner. So the only things that matter are these two, right? These are the legs of the triangle because we already have the hypotenuse as the one that's 29/6, and the other two are the two legs. And so to find the area, we just multiply these two together and divide by 2. So that would be 7 times 10 over 2 times 3, and then divide by 2. So let's see, is there a nicer way to write this? I guess it's 35/6. Sure. There's no way to simplify that, right? I don't think so. Okay, is that our answer? Yeah, it is. I guess I should say inches squared because, yeah, well, whatever. I don't care about units. I'm a mathematician. Back to Luke.
Man, I just wanted to add, I think that's very clever. Whenever people do this in a way that's more clever than me, I like to point it out. I was going to go and convert them all into stuff over 6 and then look for a Pythagorean triple I recognized. But it turns out that exactly what Eli did, that's the only important thing, which is the hypotenuse. So you just knock out the hypotenuse. And sometimes decimals are better than fractions. I'll be honest, when he was doing it at first, I was like, this is such a bad idea. Those decimals would be disgusting. But then once you got it, it was like 5 minus. Okay, that's obviously the biggest. You're done. So I just wanted to say well done. Okay, bounce it back to Luke.
All right, so now we have a circle problem, and we have in the diagram shown the larger circle has a diameter of 10 feet, and the smaller circle has a diameter of 6 feet. What is the area in square feet of the shaded region? Express your answer in terms of pi. So this circle right here is going to have a diameter of 6 feet, which means its radius is 3 feet, which is the thing we care about more frequently a lot of times. And then for this bigger circle right here, we're going to have a radius of 5 feet because the diameter is 10 feet. So the shaded region, I'm pretty sure, is this region right here. This little circle thingy thing. So what we're going to do is we're going to find the area of the big circle, and then we're going to find the area of the small circle, and we're going to do big circle minus small circle, and that will be our answer because that will give us all of this area in here. So the area of the big circle is a circle with radius 5. So the area of a circle with radius 5 is pi r squared, or 25 pi. I could say 25 pi feet squared, but I'm just going to leave the units out like Eli did last time. So the area of the big circle is 25 pi, and then the area of the small circle will be 9 pi, or 3 squared pi, because the area is pi r squared again. So our final answer will be 16 pi feet squared. I'll add the units this time. Hopefully I got that right. All right. And yes, that is our answer.
Nice. I guess you actually care about what dimensions you're talking about. If I was like building a bridge or something, I'd just mess everything up because I'd like randomly put in feet and meters or something. I don't know. But I just care about the numbers. That's what's important. And here we have a number question. That's great. Addison is 31 years old and her daughter Madison is 6 years old. How many years will Madison's age be half of Addison's age? Okay, I never really liked these kinds of questions because it was always really weird to think about. But I think the main thing that you always have to do is like choose a base year and then go from there, because otherwise it gets really confusing. Um, okay, so let's say in how many years, that's like it's been T years. Uh, then we have, let's see, Madison. Okay, uh, that would be 6 plus T, right? And that has to be half of Addison's age, so half of 31 plus T. Now, I mean, there must be like a clever way to do this, but I'm just going to solve the equation. We get this, blah, blah, blah. And then subtract out, we get T equals 31 minus 12, which is 19. So that's the number of years, and that would just be our answer. Let's see, was there something interesting I could have done?
Yeah,
Yeah, probably.
I think what people usually do with these problems is the difference between the years is always going to be constant. So Madison will always be 25 years older than
Mm.
Addison. Sorry, Addison will always be 25 years older than Madison. So if Madison's age is going to be half of Addison's age, that means that one of them has to be 25 and one of them has to be 50. So this happens 19 years from now because 25 minus 6 equals 19. So you kind of like focus on the difference between the two numbers, and that's how you can figure it out without using all the algebra.
Yeah, that's really, really clever.
Yeah. All right.
Okay.
Moving on to the next problem. If x minus 15 is 80% of x, what percent of x is x plus 15? All right. So we could do all of this math and try and figure out what x is equal to, or we could try and be smart in this case. So x minus 15 over x is equal to 0.8, right? So we know that x over x minus 15 over x, so just separating these things, is also equal to 0.8. So this is 1. So negative 15 over x is equal to 0.2, or 15 over x, negative 0.2. So 15 over x is equal to 0.2. So the reason why I wanted to find what 15 over x is equal to is because we want to find what x plus 15 over x is equal to. And if you look at this, this is actually equal to 1 plus 15 over x. So my entire motivation for all of this was seeing that we have x minus 15 right here, and we have x plus 15 right here. And it doesn't seem just random that they put 15 in both of those. So we can do x plus 15 over x is equal to 1 plus 15 over x. And we know that 15 over x is now 0.2. So our answer is going to be 1.2, but we want a percentage. So our answer is going to be 120%.
Yeah, I actually think you could think of this basically the same way, but without even having to write anything. Because you could say like, okay, if x minus 15 is 80% of x, that means I've subtracted 20% of x. If I'm adding this back, I'm adding back 20% of x. So now I have 1.2 of x. And it really does not matter what this 15 is. Obviously, writing out the equations makes it really clear that this actually works. But you can also just say, if I subtracted something and I got 20% less, if I add it, I'll get 20% more. And then you're just done, like magic. Let's see if that's the right answer. Of course it is. On to question number 13. Okay, a long question. Here we go. Charlene is looking for a part-time job from 3 local businesses. Al's Avocados pays $250 a week, no matter what. Okay. Bertha's Burritos pays $20 an hour. Carl's Cantaloupes pays $15 an hour for the first 10 hours, $25 an hour beyond that. Okay, Charlene's desired number of hours per week would pay her the same at Al's and at Carl's. How much would she make per week if she took the job at Bertha's? So let's just say the desired number of hours per week is H. And we know that these are equal. Okay, well at Al's it's just 250. So we can, that's easy. For Carl's, it's like the first 10 are, okay, 150, right? Because it's $15 an hour for 10 hours, so that's 150. And then $25 an hour beyond that, so 25 times H minus 10, because these are all the hours beyond 10. Okay, so solving this in our heads, this would be 100 divided by 25 is 4, plus 10, H is 14. Okay, great. So then we just have to like plug this in, 14 times 20, right? So 14 times 20 is 280. Is that all it is? I think so. That's how
Yes,
much you would make. Okay,
that seems right.
is that our answer? My slides would load. Looks to be on Luke's screen.
Yes, the answer is 280. Alrighty, moving on to the next problem. Problem 14. I feel like we're getting a little bit more difficult now. We can't just pass immediately back and forth to each other. So Amy and Bob each own a square plot of land. Amy's plot measures 75 meters on each side, while Bob's measures 25 meters on each side. What is the ratio of the area of Bob's land to the area of Amy's land? Okay, so this is a very key math counts concept that they bring up in a bunch of different problems that they have. So we know that the ratio of the side lengths of these two sides is 1 to 3, right? Because all we care about is the ratio of the areas, and the ratio of the areas comes from the ratio of the side lengths. So instead of saying it's 25, 25, 25, and 75, let's just say that we have like a square plot of land with side length 1 meter on each side and a square plot of land of length 3 on each side. We're dividing every single dimension by 25. And if you divide everything by 25, they're both getting the same amount smaller and the side lengths are getting the same amount shorter. Okay? So now we have two different squares. And obviously at this point, we could just calculate this out and see that we have 9 right here as the area of this one and 1 as the area of this one. So our answer is going to be 1 over 9. And something that's really important with this problem is all we cared about was the ratio between these side lengths. All we cared about is that 25 over 75 is equal to 1/3. And from there, we can square 1/3. 1/3 squared is going to be equal to 1/9. So 1/9 is going to be our final answer. And yes, indeed, the answer is 1/9. All right.
Cool. Yeah, so that's good stuff. Meanwhile, I'll just say Eli is currently trying to figure out. We had a glitch on the online whiteboard thing we're using, so Luke's gonna keep on going for a while.
Alrighty. Let's get on to problem number 15 now. Carson is pushing a broken shopping cart in a series of straight line segments. After every meter he pushes it, a wheel locks, causing an instantaneous 15-degree turn to the right before it continues forward. Eventually, he finds himself back where he started for the first time. How far in meters has he pushed the cart? Okay, so what we have here is a shape that has every single side length equal to each other. And what we know is that similar to a triangle has like 180 degrees, right? Square has 90 degrees in each side length. A pentagon has 108 degrees in each side length. This shape is something like that, but in this shape, we have 15 degrees on the outside of each of these angles, which means that on the inside of these angles, we have 165 degrees. But actually, the angle that's on the inside is not as important as the angle that's on the outside. Because if you think about it, the angle on the outside, we're turning 15 degrees each time. So eventually, after a certain amount of times, we're going to be facing the exact same orientation that we were facing originally. In other words, we're going to turn 360 degrees. You can think of it as if we were the person who was, if we were Carson, eventually we would do enough 15-degree turns where we curl all the way back and turn 360 degrees. And after we turn that 360 degrees, we are going to be back where we started. We're not going to be anywhere else because this is a normal shape that has all the sides equal to each other. So now we just need to figure out how many times we need to turn in order to get back to our original time. So we have 15 degrees each time we turn, and a total of 360 degrees are needed to make a full circle. So 360 divided by 15 is going to equal 24. So we're going to do 24 turns each time, which means that we're actually going to have 24 meters of pushing our cart in order to get back to the beginning. So 24 meters will be our answer. And checking this, we do indeed get 24 meters.
Yay! Okay, I just wanted to say this particular question, sometimes the way people go about doing this is to use the formula for some of the angles inside a n-gon, which is actually how you got that. We're using that 165. That would be really, really cumbersome. So this particular technique that Luke just used here that's the slick one. It's this called the sum of the exterior angles. Eli, unfortunately, is still trying to figure out the thing. He's back.
Ah,
Eli's
I figured
back.
out the
Okay,
thing.
here we
Okay, I
go.
got it. I got it. Here we go. Okay, so we're on which question? This
16.
question. Okay, here we go. Jamie has a small business selling pies and cakes. Okay, pies. This is perfect for Pie Day. Wow, okay. He sells pies for $10 each and cakes for $12 each. Okay, it must be because of Pie Day that the pies are cheaper. This makes sense. His revenue from selling cakes is the same as his revenue from selling pies. If he sells 240 pies in a month, how many cakes does he sell? I want to try to do this without writing any equations. We'll see if I can. But the ratio then is like 12 to 10, right? He has to be selling like a 12 to 10 ratio of pies to cakes if he's selling them at $10 to $12, if the revenue is the same. So 240 pies, if we just apply this 12 to 10 ratio, that means we divide by 12, multiply by 10. I think that would mean 200 cakes. And that's it. So is that the answer? Yeah, it is. Why do I even need bit paper? I can just do this all verbally.
Oh man! Actually, I want to say, whenever I saw when you were doing this, I was like, "Oh no, we gotta be really careful. We don't have the wrong way." But I like what Eli said earlier, which is like, "Oh, it's Pi Day, so the pies are cheaper." So that's how you have a sensibility check because it's like if there were more cakes, that would be like, "No, no, no, something screwed up." But yeah, nice.
Alrighty. Moving on now to problem 17. A rectangle has a perimeter of 26 units and two of its side lengths sum to 20 units. What is the area of the rectangle? Okay, so we have a rectangle like this, and the entire perimeter, so let's say that this is the height and this is the length right here. We know that the height plus the length, 2 height plus 2 the length, is equal to 26. So that means we also know that height plus length is equal to 13. So that means that we couldn't have added the height plus the length to get the two side lengths equal to 20 units because that's 13 right here. And that's just going to be half of the perimeter, and this is not half the perimeter. So we know that immediately. So one of the side lengths, we can choose which one is going to be equal to 10. Let's just say length is equal to 10. And then that means that height is equal to 3. We could have just as well chosen that height was equal to 10 and length was equal to 3. We would have gotten the same answer because we just need to do length times width. So we get length times width equals area. So our area is going to equal 3 times 10. And 30 is going to be our final answer. And checking that, we indeed get 30. All right, back now to Eli for the next one.
I mean, they even bothered saying units squared. They didn't have units to begin with. Like, why? It's just pointless. Okay. But good, we have another number question. How many three-digit positive integers have 3 digits whose product is 18? Okay, this isn't too bad. So we have 3 digits, right? A, B, C, something like this. I think the main thing to remember is that A cannot be, well, it couldn't be 0 anyway. So whatever, this is not anything. Because if the product is 18, okay, obviously the product is not 0. So A times B times C is 18. How many ways can we do this? It's really just a question of how many ways can we do this? Yeah, with order mattering. And I guess maybe the prime factorization of 18 will help, but I think this is just going to be a bunch of cases anyway. So this is 2 times 3 squared, right? So yeah, if one of them is 1, then it's just the number of divisors of 18, which, okay, I don't know if I can use this thing, but like the idea is, how many 2s do you have? How many 3s do you have? These are like independent choices. You can have either 0 or 1, 2, or 0, 1, or 2, 3s. So that's like 2 choices times 3 choices. So 2 times 3 is 6 when you have a 1. If you have a 2, then this would be okay, I'm just saying basically cases of what A is, right? If A is 1, then I think you get these 6. If A is 2, then you should get.
Ooh, I just want to jump in. I just want to jump in just to save a little bit of time. The problem though is that I think you also get 1 and 18 as some of your cases.
Okay, no, this is
Because at
true.
first I was trying to do the same
Dang.
thing. I was trying to do the same thing, and I was like, oh no, I cannot be that clever. Because also, like the order even matters. So you might need to go slower.
Oh,
But
yeah,
I don't know
dang.
the answer to the
Okay.
question yet. Okay,
I
keep
guess
going.
this is really just like a writing everything out thing. I'm not sure there's a nicer way. So okay, but I do want to start maybe with just one of them being 1, and then like just seeing what happens there. So if you have 1, then you could have like, okay, the next thing could be 1, but that can't happen because then you have 18. So it could be 2 and 9. Obviously 1, 9, 2. This also works, and any permutation of these. So actually, I'm just going to forget about that. Just going to say times 6. Then you could also do 1, 3, and 6. And again, times 6. And let's see, the next thing would be, is there another divisor? No, I don't think so. There's no other divisors of 18 that we can use. Okay, so let's forget about that. Let's say that one of them like is 2, but it's not one of the ones we've already done. Well, it just seems like the only other way is we can't have a 9, right? Because that would mean the last one's 2. So the next one has to be a 3. If you have 2 and 3, then the last one is 3. And I think this is all you can do. If you have a 3, then you're either going to have a 2 or a 6, and so you're done. So I think this is actually everything. And this one, instead of being multiplied by 6, would be multiplied by 3, because you just choose where the 2 goes. And so this just means 6 plus 6 plus 3. I believe that's 12 plus 3 is 15. So that should be our answer. Okay, yeah. I guess this actually required some thought, and it wasn't super clever, but it got us to our answer. Let's see if 15 is right. It is. Okay.
Yeah. I think the thing here is that unfortunately, when we try to be too clever, sometimes it doesn't work. So I like how Eli was like, "Ah, man, we gotta actually list this thing." So, but I also think that one of the things you ended up doing is you ended up just listing them in sorted order. I think Luke, you did the opposite sorted order. It looks like that. So it looks like Luke was doing it where he was listing these triples where it's like big to small, right? And then Eli, yours were sorted from small to big. But as long as you're consistent, then you can do the times 6 times 3 thing. So it's cool. Yeah, great.
All right, moving on to the next problem. And also, by triples, I don't think I consciously sorted them in like biggest to smallest. I think I was just doing it randomly, whatever came to my head first, but it happened to be like that. Okay, the first and 21st terms of an arithmetic sequence, of an arithmetic progression, are 26 and -4 respectively. How many positive terms does the progression have? Okay, so let's say that a is equal to the first term, and a is going to be equal to 26, and then the last term is going to be -4. So let's say that our terms go like a plus r, a plus 2r, because this means that we're going to have an arithmetic progression because we're adding r every single time we have another number. So our last term is going to be a plus 20r. Now you might think it's going to be a plus 21r, but it's actually going to be a plus 20r because our second term was a plus r, our third term was a plus 2r, and so on. It's going to be one less than our original one. And actually our first term contains 0r, if you think about it. So a plus 20r is going to be equal to -4. Now we want to figure out what r is equal to, because then we can go back and say, okay, the 20th term, was that negative or positive? The 19th term, was that negative or positive? Based on the r that we have. So a is equal to 20 in this equation. So 26. So 26 plus 20r is going to be equal to -4. Okay, now we subtract 26 from both sides of the equation, and we get 20r is equal to -30, and r is equal to -3 over 2. Yes, -3 over 2. So we want to figure out the last term that's going to be positive, and then every other term after that will be negative. So writing the 21st term right here, the 20th term will be 3 halves plus this right here, because it's going to be a plus 19r, not a plus 20r. So 3 halves plus this is going to be equal to -5 over 2. -5 over 2, add another 3 halves. So this is the 21st term, 20th term. Then we're going to have -1 right here for the 19th term. And then the 18th term is going to be 1/2. So every term from the first term to the 18th term is positive. So our final answer is going to be 18. All right. And checking that, we do indeed get 18.
Nice. All right. On to question number 20. A rhombus with area 60 inches squared has a diagonal of length 6. Okay, so rhombus looks like this kind of thing, vaguely. And diagonal, which diagonal should it be? Let's go with this one. I feel like this may be wrong, but let's go with this. Okay, this is 6. And the area is 6 feet. Okay. How many inches long is the side length of this rhombus? I think there's probably some formula that I'm like forgetting that makes this really easy, but I don't know what that formula is. So I think I'm just going to go and try to figure things out. I think one thing that is true in a rhombus is like the diagonals are perpendicular. Uh, this is true. And they're also like, it's a parallelogram, so this would cut it in half. So this is 3 and 3. And so if this is h, that means that the area of this parallelogram would be like 3 times h times 4, well, divided by 2. So yeah, because each of these has area 3 times h over 2, right? And there's 4 of them, and they all have the same area because they're all that same 3 times h over 2. So we get 6h, right? 3h over 2 times 2, and that's equal to 60. So h is equal to 10. And so now we have 10 here, 10 here. And a side of this rhombus, okay, well, now we just have to use the Pythagorean theorem because we have a 3, 10. And so that would be 100 plus 9. Square root of 109. Is there like a nice thing for this? I don't think so. So, okay, square root of 109 our answer? Yeah, ugh, terrible question. I always like nice answers. I can't give you things like this. It's crazy.
Yeah, all right. Great job, Eli. And the next question is question 21. Haley tosses a fair coin 5 times. What is the probability that at least 2 consecutive tosses show the same result? Express your answer as a common fraction. Okay, so let's say hypothetically that our first toss was tails. Then our next toss would need to be heads, because if it was tails, we would... Oh, sorry. Let me slow down. What is the probability that at least 2 consecutive tosses show the same result? So figuring out if 2 consecutive tosses show the same result is pretty difficult. We would have to look at all the different places where 2 consecutive tosses could show a same result. So instead of finding that, let's find patterns where 2 consecutive tosses never show the same result. So we're going to have no same results on consecutive tosses. So if this were to be the case, if we were to flip a T first, then we would have heads here, then tails, then heads, then tails. This is what we would need to have if we had the tails first. We couldn't have anything else because then we would have 2 consecutive tosses. So we could have it like this, or we could also have it where we have heads first and then tails, heads, tails, heads. And these are the only 2 possibilities. Any other way, we're going to have 2 consecutive either heads or tails at some point. So the probability that this first one happens is 1/2 for each of those times. So 1/2 times 1/2 times 1/2 times 1/2 times 1/2. And this is equal to 1 over 32. Similarly, this is also equal to 1 over 32. So 1 over 32 plus 1 over 32 is going to be equal to 1 over 16. And one more way you could look at this is every toss after the first one has to be different than the one before it. So the first one, you can do whatever you want. And then every toss after that has to be different than the one before that. So there's a 1/2 chance for each of these tosses to be different than the one before it. So multiplying 4 1/2s by each other, this is really the same thing as what we just did, but we get 1 over 16 again to reinforce our answer. And, oh, I'm sorry. So we found out that, so yeah, that was wrong. 1 over 16 is wrong. So we found the probability that no 2 consecutive tosses show the same result, but really they asked us that at least 2 consecutive tosses show the same result. So we're going to do 1 minus 1 over 16. 1 minus 1 over 16, and that's going to be equal to 15 over 16. This is a reminder to you guys to always read the question before you do it so you don't make dumb mistakes like what I just did.
All right, but it looks like you got the right answer nevertheless. And so we can move on to question number 22. And okay, talked about reading the question. Well, now I have to go read a long question. This is great. Okay, an elevator in a high-rise apartment takes some fixed amount of time to start moving at the beginning of each trip. Okay, after starting up, it travels at a constant speed until reaching its destination. A ride from the 20th floor to the 26th floor takes 15 seconds, while a ride from the 2nd to the 34th takes 1 minute. What is the speed of the elevator when the elevator is moving at floors per second? Okay, now I think you could write equations for this. balloons to celebrate equations. But instead, I'm going to try to do this without equations again. So, okay, 20th floor to 26th floor. That means I'm moving 6 floors up. So that's 6 floors I'm moving up. But then the other way, I'm moving up, let's see, 2nd to 35th, I'm moving up 33 floors. Okay, so if I take the difference between these two, the difference in time, because the fixed amount of time at the beginning would cancel out. The fixed, that doesn't matter. So the time that it takes me to move up 33 minus 6, which is 27 floors, should be the difference of 1 minute and 15 seconds, which is 45 seconds. Okay, so that means 27 floors in 45 seconds. I can just divide them. So I can say how many floors per second. Is that, so the question is, yeah, what's the speed of the elevator in floors per second? It's just 27 over 45. Whatever that is. Okay, so let's see, there's a factor of 3. So this would be what, like 9 over 15. Okay, there's 2 factors of 3. Great, that's great. 3 over 5. Okay, 3/5 of a floor per second. That seems reasonable. Is that the right answer? Yeah, it is. Great. Okay, back to you, Luke.
Alrighty, on to problem number 23 now. More and more word problems. So after placing a delivery order for pizza, 5 friends realize they've run out of soda. They decide that some will go buy more soda while the rest will wait for pizza, with at least one person assigned to each task. And how many ways can the 5 friends divide themselves between the 2 tasks? Okay, so one thing I do not like when I see a problem like this is that there are no numbers, but we will work through it anyways. So some will go buy soda. Oops, I meant to draw an S. So some will go buy soda, and others will wait for pizza. And the 5 of them are going to split themselves between each task with one person assigned to each task. So let's say that the names of the friends, they have really creative names, and they're A, B, C, D, and E. These are the names of the friends. So let's just take person A, for example. Person A can either wait for the pizza or wait for the soda. So he has 2 options. And so does person B, as well as person C, person D, and person E. They all have 2 options. They could wait for the pizza or the soda. So there's 2 options for person A times 2 options for person B times 2 options for person C times 2 options for person D times 2 options for person E. Because for each option that person A chooses, pizza or soda, person B could also choose either option, pizza or soda. That's why we multiply them like over here. So 2 times 2 times 2 times 2 equals 32. So that should be our final answer. Well, actually, we have one other thing. It says with at least one person assigned to each task. And in this case, we could have had all 5 people assigned to pizza or all 5 people assigned to soda. So we need to be really careful, read the question again, and check to make sure we did the right work. But what we did is incorrect. So we need to subtract 2 for the cases when all 5 people are either at the pizza or all 5 people or at the soda. So 32 minus 2 is going to be equal to 30. And this is going to be our final correct answer, 30. All right, let's check just to make sure. And indeed, the answer is 30, although you cannot see it on my screen, only on Eli's. All right, back to Eli.
All right, back to me. Number 24, we have A and B positive integers such that 1 over A plus 1 over B is 2/3. What is the sum of the 2 distinct possible values of A, B? Okay, at least they tell us that there's only 2 ways. That'll make things easy. If we find the 2 ways, we'll be good. So now we just have to find the 2 ways. Okay, what's the best way to do this? Well, I know that A and B, like one of them has to be divisible by 3 because I have to get a 3 in the denominator. I could, multiply everything out and I get an equation, and I could probably factor or something. That might be the way to do this. I'm trying to think, is there a better way? I don't know. I think I'll just do that for now, and then I can be informed if there was a better way later. So let's see. We would get, if we multiply everything by A, B, and 3, so multiply everything by 3AB, then we would get 3 times A plus B on the left. And on the right, we'd get 2AB. And if we subtract, we'd get 2AB minus 3A minus 3B. And then here, we should probably like add something, right? And this is what people do. So Yeah, maybe I also have to like multiply through by something. Yeah, maybe I'll make this 4 and 6 and 6. It's all equal to 0 anyway. Um, so something like this. Yeah, this is a 4 now. Uh, and I think this is a thing to do. And what should I add? Well, it should be like 2a minus something, 2b minus something, and the minus something should be 3. Yes, maybe. Well, okay, now I have to write
I
this.
think you're on a good track. This is pretty good. So far so good. I see what you're doing. Maybe like right. Do you guys have do you have an empty screen in the next one or no? Oh, you don't do it that way. But like, do you have a way to move it because you probably need a little bit
Yeah,
more
of course,
space.
I can go like this. Okay,
But
here
there
we
you go.
go. I think plus 9 should work. I mean, it should be 2a minus 3, 2b minus 3 or something, right? Yeah, that works. Of course. Okay. So anyway, this is equal to 9. And so I get 9 over here because I added 9 to both sides. This is, so if I subtract everything over, multiply by 2, and then add 9 to both sides, this is what I get. This factors nicely because I get, the 4ab here, minus 6a minus 6b plus 9. And so now, okay, the point is 9 only factors in like a few ways. And by a few ways, I mean only 3 ways that are essentially different. And what's actually cool about this is that these two things are odd numbers. 2a minus 3 is some multiple of 2 plus an odd number. Same thing with 2b minus 3. So these are two odd numbers. No, that doesn't tell me anything anyway. 9 is already odd. Okay, whatever. So the way I can write this is 1 times 9 or 3 times 3. So actually, yeah, or 9 times 1, but A and B, we don't care about the order because it just asks for the different products A, B. Okay, so that's the thing that makes it only 2. So if we have 2a minus 3 is 1, we would get A is 2, 2b minus 3 is 9, we get B is 6. Yeah, that sounds right. Okay, so that would give us a product of 12 in that case. And then in the other case, we'd have 2a minus 3 is 3. So A is 3. No. 4. No. Yes. No. Okay. What am I thinking? Oh, yeah. It's just 6 divided by 2, which is 3. Yeah. Okay. And then B is also 3, of course. And then the product is 9. Okay. This is what happens when I try to do math in my head. It does not end well. So anyway, I just add the two things, 12 plus 9, which is 21. That's what it asks for, is the sum. Right? Sum, great. Okay, I think my answer is 21. I'm just gonna move the slide over before things go awry. And things went awry. So there you go. I think Luke has on his screen that the answer is 21. Let's
Yes,
see if that's right.
the answer is indeed 21. Great job, Eli. And moving now on to
Ooh,
problem
can I
25.
just jump in first? I just want to jump in
Yeah.
first only because Eli, you did this thing really fast. Well, obviously, you knew what you were doing. Uh, I'm sure there might be some people watching this who are like, "How the heck How did you know that times two?" And I don't know if you can draw anymore because I don't know if your thing got nuked. Is your thing still there or is it dead?
Um, it should. I think I know how to fix it. So
Okay,
if
okay.
I, yeah. Well,
Well,
okay.
okay, while you pull it up, I'll tell a joke. Not a joke, I'll tell a fun story, right? Because actually, what Eli just did is a pretty tricky thing. Ooh, this is the secret. You're seeing the secret workings of how our stuff works. So let me hide Eli temporarily. If anyone wants to know how we run all of our show, it's because we have some technology. But in any case, the deal is that what he just used, many people call SFFT. Does anyone know what that stands for? You can type it in the chat. So people will use SFFT. Oh, yes. If you were wondering how to react here, don't raise hand, just like send messages to chat relay. But yeah, so there's the Simon's favorite factoring trick. Does anyone know who Simon is? So the funny thing is, whenever you hear about a math theorem or something, you're like, yeah, Simon was probably some Greek guy from like 3,000 years ago. But no, Simon actually turns out to be a guy who lives in San Francisco area. He actually coaches kids in math. So I think Simon's favorite factoring trick off with the name SFFT because yes, indeed, he was a guy from who was on this AOPS forum chatting with stuff and suggesting things. So now that particular trick that's going on, San Francisco factoring trick. That's funny. Oh no, I see. That sounds good. Right, but so Yeah, so Eli's thing didn't come back yet. But because this is a point which is quite useful, Luke, would you be willing to just like talk through how one thinks through this? Because Eli first cleared the denominators and he wrote 3 times a plus b, which I know that some people might get confused because like, well, how is it 3 times a plus b anyway? It's actually 3 times b plus a, but that's the same thing. So like, when you multiply both sides by 3ab, oh, Eli's still trying to get it in. Oh man, we need to get a different whiteboard program. But yeah, so when you get this like 3a plus 3b equals 2ab, Luke, would you be willing to walk through the thinking process of how this works?
Yeah. All right. So what Eli did is he multiplied 3ab by both sides. And then when he did that, we had 3a plus 3b equals 2ab. So from this point right here, it's pretty hard to find the solutions to the equation. We don't really have any comprehensible way we could go about this, but we can use Simon's favorite factoring trick to factor it because then we have a lot better grasp on how to solve this equation. So it's sort of like factoring a quadratic in a sense, right? Like x squared minus 5x plus 4, for example. Like factoring this, that's kind of the comparison to over here. But over here, we have 2 variables instead. So the first thing to do is get everything on the same side of the equation. 0 is equal to 2ab minus 3a minus 3b. And then what we're going to have is we're going to have 1. So this is going to be equal to 0. And we're going to have one of these two things that we're multiplying have a as the first term. And, oh wait, so what he did actually, sorry, is he multiplied everything by 2. So then it was equal to 4a b plus 6a plus 6b. And the reason why you do this is because you want to have the first term and the two things that we're multiplying by each other to be equal. So we have a 2a over here, and then we have a 2b over here. So we have something that looks like very symmetric for a and b, which is very, very nice. And then the two other terms we need to make sure that we have are negative 6a and negative 6b. So to get the negative 6b, we can subtract 3 here, and then we get a negative 3 and a negative 2 over here. And then we can also subtract a 3 over here to get our negative 6a. So 2a minus 3, 2b minus 3. But then you also have this constant term over here. So negative 3 times negative 3 is going to be a constant term equal to 9. So we need to add 9 to both sides of the equation to get this equal to each other. So this is actually going to be equal to 9. And the key idea to think about when you're doing all of this is that we just have to make sure we have these 3 terms, and then whatever the constant term is, we can add it back in. And that's sort of like the premise of Simon's favorite factoring trick. You have 3 terms with these 2 different variables, a and b, and you can actually factor them a lot more nicely and easily than you usually thought you could. So yes, that is Simon's favorite factoring trick.
Cool. Yeah, thank you, thank you. I'll also add like sometimes the way I think about this, because when I look at these things, I actually don't always know the times two. Here's where unfortunately I can't write. But like if I didn't know, ooh, Eli's back. So let me just throw Eli on just because not everyone can see all of us. But yeah, so somehow it's just when I look at this, when I don't know what to do at first, if I just had like the 2ab minus 3a minus 3b, the first thing I do is I just take the first 2 terms and I try to factor something out of that. And I get fractions. I get like weird fractions. But then the fractions I'll clear up later. I say this because on this one, it's like Eli had this stroke of apparent genius to people. Like, what? Why times 2? So I want to say, even if you're not clever enough to times 2, there's a way to look at this and be like, I just want to take the first 2 terms and get something out of it. Okay? So I could do that. Yeah, this and I got some fractions. Maybe Eli, why don't you finish off with this? Because this is another way of seeing it where you get like weird fractions, but then it will solve the problem.
Yeah. So if you factor out 2a from the first thing, just because you want to factor something out, you get b minus 3 halves in here. And so you say to yourself, okay, well, I want to make a b minus 3 halves somewhere else. I already have a b. So why don't I just like manufacture a 3 halves? So I'm just going to put a parentheses here, put a minus 3 halves, and then see what I have to do to make this actually true. So what did I just do? I basically added a negative 3 times minus 3 halves, which is 9 halves. So if I want to get rid of that, I just have to subtract 9 halves. And this is, I think, a common thing actually when you're solving like some quadratic equations where you have a thing in the front, like 2x squared plus whatever. And then you like change the order of them so you can factor them and stuff. So anyway, we have this here. We have the b minus 3 halves minus 9 halves. And all we have to do is now factor out the b minus 3 halves. We get b minus 3 halves times 2a minus 3, and then minus 9 halves. And this is all equal to 0. If we multiply through by 2, then something really nice happens. On the right-hand side, we just get 9 if we add the 9 halves to both sides and multiply by 2. And on the left, well, we can bring the 2 inside of b minus 3 halves. And then we don't have those weird denominators anymore. So we get 2b minus 3 times 2a minus 3 is equal to 9. And that's exactly the same as we got before. And here, maybe it makes more sense. Like, why did we multiply by 2? Well, because we had things like 9 halves and 3 halves, and we just want to get rid of those. And then once we have
Yeah.
this, then we can actually do the number theory stuff with looking at how to factor 9 and all that.
Yeah, thank you so much. I mean, because you see, sometimes like Luke was doing it where, these kinds of like observations, oh, I can do this, I can do that, I can make it work. And I see sometimes the way we do these problems here is like we seem to have these strokes of genius. But I wanted to show everyone in the audience, like, suppose you didn't have that stroke of genius. Suppose you just wanted to beat the whole thing up. Then it actually always can be done with what you just saw there. Okay, but now back to Luke, because then we're going to go forward.
Alrighty, question number 25 now. Half of the students in Dr. Papa Nicholas's class, I think I said that right, play the piano, and a third of them play the cello. If there are 3 students in the class who play both, and 20 students who play neither, how many total students are there in Papa Nicholas's class? Okay, so let's say the number of students in the class is X. So we have X students in the class. And we know that X over 2 of these students play the piano. So X over 2 play the piano, and X over 3 play the cello. So in total, the number of people who are going to play instruments is X over 2 plus X over 3. But think about it. Actually, it's going to be less than this because we overcounted because 3 students play both instruments. So we counted 3 students who play instruments in this, and then we also counted them in here. So we need to subtract by 3 to get our actual count of the number of students who play instruments at all. So adding all these things together, we get 5x over 6 minus 3 is the total number of people who play instruments at all. And then we are also told that 20 students play neither instrument. So that means that x minus 5x minus 3 is going to be equal to 20. Because this represents the number of people who play instruments at all, and then x minus this represents the people who don't play either instrument at all. So x minus 5x over 3, minus 3 is going to be equal to x over 6 plus 3 is equal to 20. Ooh, I look a little hidden right now. All right, x over 6 plus 3 is equal to 20 based on that previous equation. So now we know that x over 6 is equal to 17, because we subtract 3 from both sides of the equation. So x over 6 is equal to 17. Multiply both sides of the equation by 6, and we are left with x is equal to 102, which hopefully should be our final answer. And checking this, we indeed get 102. All right.
Yeah, I just wanted to quickly say how I thought about this question, because what you did was obviously great, and you had all of this interesting ways of using the information to make equations and stuff. But I like what you said about making x the total number of students, but I just like drawing diagrams. I just find it's much easier to keep track of what's going on. So, make the cello, piano diagram here. The overlap is 3, and I know that this whole thing is x over 3. This whole thing is x over 2. So this part is x over 3 minus 3. This is x over 2 minus 3. And on the outside is 20. And I know that the whole thing, including the outside, has to be x because that's the number of students. And so then I can write, x is the sum of all of this, and then you get the same answer. But I just like that this is, very organized and all of that. But you can actually do everything you just said as well, just by looking at like what actually has to be true, especially with this overcounting stuff. That was really, really clever. But I think this is just, I don't know, helps me see what's going on. Okay.
Yes.
On to the next question, number 26. We have an equation, a quadratic equation, 6x squared plus 11x minus 10 equals 0. A and B are the 2 solutions. What's the value of A plus B minus AB? Okay, so this is a fancy thing that maybe also if you've seen before, makes a lot more sense than if you see it for the first time. But okay, so I could solve this probably, use the quadratic formula or whatever, and get some values for a and b and then plug in. That just sounds like unfun to me. I don't know about you. I'm not in the interest of solving a bunch of quadratics all day. So let's see if we can find a more clever way. And the more clever thing to do is, okay, I'm just going to divide everything by 6 because I don't like having a 6 out in front. That's just weird. So let's say we have x squared plus 11 over 6x minus, I'll just write it as 10 over 6 equals 0. Okay. Now I know that there's two solutions, a and b. And if you remember how we normally solve quadratic equations, we factor things. And in particular, we know that if there are two solutions, then this has to look like x minus a times x minus b equals 0, where a and b are those two solutions. And so this thing is equal to this thing. If you wanted to see like more exactly why that has to be the case, you could also say like try dividing this polynomial by x minus a, and then the remainder is 0 because the remainder is a constant, but the constant has to be 0 by plugging in x equals a. And you could do all of that, but I think you can believe that this is what we have to get here. And when we do that, you can actually expand out this thing over here. You get x squared minus a plus bx plus ab. And so just by comparing coefficients, this ab has to be negative 10/6, and this minus a plus b has to be 11 over 6. But if we look at what we want a plus b minus ab. So that just means a plus b is negative 11 over 6. And then minus ab, well, ab is negative 10/6, so that's plus 10/6. So I think I'm left with negative 1/6. Is this incorrect? Have I done something wrong?
No, yeah, that's right. I had the wrong thing on my screen.
Okay. Cool. Let's see if negative 1/6 is our answer. Yeah, it is. Cool. Awesome.
Alrighty. Let's move on now to problem 27. We're getting to the very difficult ones now. And Odie the frog wants to hop from 1-1 to 11-11. On each hop, Odie can jump either 1 unit upward or 1 unit to the right, but only to a location having at least one odd coordinate. How many different paths can Odie take to reach his destination? Okay, so we can either jump 1 unit upward or 1 unit to the right, but only to a location having at least one odd coordinate. All right, so we're starting at 1-1. Immediately we can either jump right, or up to 1-2 or 2-1. And then this spot right here is going to be a place that we cannot jump. So we do not have a choice of where we're going to go after this. We're going to have to go up. Okay, so we're going to have to be at one of these spots. And we need to find a way to figure out where we're going to hit odd spots and what's going to happen at those, where we're going to hit even spots and what's going to happen at those even spots, which seems pretty difficult right now. So this is an even spot right here, 2-2. And then if we move up 2 units, this is also going to be an even spot. This is bad. So if we were at this spot, right here, we would have to go to this spot.
I suggest since the questions are getting harder, we put more people on the screen. Because then the two of you can solve them together. This is pretty good. Because I get to see all the things happening. So I'm like, I think that both of you are thinking at the same time, and this might work pretty well.
Yes. I feel like this is the point where we don't immediately know how to solve the question. We have to work through it a little bit. But I think I have an idea, hopefully. So this point right here is going to be 4-2, and then this point over here is going to be 2-4. So we run into these points after 1 hop here, 2 hops here, 3 hops here. We would hit it on our 4th hop, but we're not going to hit it, obviously. We would hit this point right here on our 2nd hop. So let's just think about a couple other points that have only even coordinates and figure out when we could possibly hit them and what's going to happen at the times that we could possibly hit them. So we have 6-2, 4-2, wait, no, I did not mean to say that. We have 6-2 is one that we could possibly hit, or 4-4, and 2-6. And we would hit all of these on our 6th hop. And how do I know that? Well, think about it. We're increasing our x coordinate or y coordinate 1 every single time. So it would take 6 hops to increase from 1, 1 to 6, 2, 4, 4, or 2, 6. Okay, now let's go back to our problem. What happened when we potentially were going to hit this 2, 2 right here is we were at this point or this point, and we were forced to go upwards. All right. Now, similarly, when we're at this point, we can either go right or up. We have a choice of where we want to go. But then we're forced from this point to go up, and we're forced from this point to go right. We have to do that no matter what. So we're in this interesting dilemma, I suppose, where our free move was right here, and we chose our free move to go up, and then our other move is blocking us go right. And the reason why that is because when we're at this odd thing right here, all these odd points, when we're at these even points that have 2 even coordinates, they happen at 6 hops, like I just said. And all the other coordinates that we could be at 6 hops are 7, 1, 5, 3, 3, 5, or 1, 7. Notice how all of these coordinates have both an odd first point and an odd second point. So we have a free choice of whether we can go right or left. But whichever way we go, as we can see here, if we go right, we can't go up, because then we would have increased our y by 1 and our x by 1, and we would then be at an even coordinate. So we have our free choice right here. We have to go 2 up at the same time. We have to go up in a block of 2. We have to go right in a block of 2. And this makes sense if you really graph out all of these even points. They're kind of scattered around, and we have to dodge them. And by doing that, we're going to go 2 up, 2 right, 2, a bunch of different directions in 2. And that's the key idea in solving this problem. So in order to get to the point 11, 11, we're going to have to go blocks of 2 to the right 5 different times. And we're going to have to go to blocks of 2 to the left also 5 different times. Okay, I was really nervous that the... Sorry, yes, go ahead.
No, you just mean up. That's all. Is there
Okay.
two right or 2 up? Yeah, that's right.
2 right. Oh, did I say 2 right or 2 left?
Yeah. No,
Okay.
it's all good. You're solving the problem. This is pretty good. And I'll also
Yeah.
say just one thing. When Eli drew the thing, I was like, it looks like you're walking around Manhattan. That's
Yes.
basically what's going on. In Manhattan, you can't walk through the sky. Well, I guess you can sometimes, but you don't walk through the skyscrapers. But it's like you got these like big blocks in between. But your key idea was that, yeah, you go 2 in each direction, and then that's it. So yeah, well, keep on going. I'll drop
Yeah.
off now because I think this is good. I mean, I'll disappear now.
Yeah. So when we're going to in blocks of 2, we're guaranteed to miss all those even points, like we said. And so we have to go 5 times right in those blocks of 2, and then 5 times left in those blocks of 2. So if you've done a decent
You mean
amount of
up?
problems... Oh, sorry. 5 times up. There's no way I did that again. Okay, 5 times right and 5 times up. So if you've done a decent amount of problems like this, you know how this works. But every single rearrangement of these 10 letters corresponds to a path that we go 5 times up, 5 times right, and eventually get to 11, no matter the order in which we did the 5 times to the right and the 5 times up. So let's just do a hypothetical path right here just so that you can see this in action. So if we went 2 times up first, go up, up, and obviously I'm not drawing this on the board, so it's not as real, but you can check this on the board as well. Right, 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 up, right, up, up, right. So no matter what way you redo this in, we're going to go up 5 times and right 5 times, each 2 blocks, which means we're going to go up 10 units, right 10 units, and get to the point 11, 11. So now we just need to find the number of ways to rearrange 5 R's and 5 U's. There's a couple of different ways you can do this. You can think of it as just 10 choose 5. If you don't know what that means, it's a little fancy formula thing. Or you can think of it as there's 10 factorial different ways we could rearrange all of these numbers. And there's 5 factorial ways we could rearrange the R's, which we overcounted. So we have to divide by 5 factorial. And then we have to divide by 5 factorial for the U's, because we could rearrange the U's in 5 factorial ways. And we consider them as all distinct, but really they're all the same. So divide by 5 factorial again. And then this is going to be equal to 252. You can do the math out for yourself, but it's equal to 252. So 252 is going to be the final answer.
All
Yes,
right.
there we
I
go.
believe I agree. That was a really, really clever solution. I just drew out the whole Manhattan thing just because I had no idea what to do. So I just like, okay, I'll label all the things I can't do. And I was thinking, okay, maybe there's some weird counting thing. Like, okay, one thing that I always do with these kinds of questions is I could label like, okay, how many ways can I get to this point? How many ways can I get to this point? And then you do the thing where like you add up all the ways that you can get from this point and this point, and then you can keep on propagating through the entire thing. I think that would be pretty terrible with this question, unless maybe I like noticed a pattern. But this whole thing of like, okay, I actually have to take steps of size two. That's really cool. Okay, on to question number 28. We have a drawing. Equilateral triangles are erected on the outside of a square. Okay, so that's what's going on here. These four equilateral triangles outside of the square. Okay, the total area of the shaded region is 100 root 3. What is the total unshaded area inside ABCD? So ABCD is the big thing. Just want the total unshaded area. That should be fine. I think we just need to find the total area and subtract 100 root 3. I mean, maybe there's something more interesting. I don't know. But if the 4, see 4 times one of the areas, okay, so 4A is 100 root 3, then that means the area of one of the equilateral triangles is 25 root 3. And there is like a formula for the area of an equilateral triangle. I'm not even sure I remember what it is, so I might as well just do it again. So let's say that the side length is S. Maybe I'll call it, yeah, I'll just say it's S. Then if we drop the perpendicular here, this would be S over 2, and this would be S here. And you may notice that this is actually a 30, 60, 90 right triangle, because I have, well, there's a lot of ways of realizing this, but this is a 60-degree angle here, and we've cut this 30-degree angle in half. So this is 60 down here and 30. And so some trigonometry tells you that this side length, the height, is actually S over 2 root 3. That's the height of the triangle. And so the area would be 1/2 times S over 2 root 3 times S over 2, because that's the height of the base. And this whole thing is equal to 25 root 3. Okay, that's nice. I can get rid of the root 3's. I can also get rid of, oh, I thought these were 5's. Okay, they're
I think,
S's. That's
yeah,
really
yeah.
confusing. Yeah,
But I also think you're off by a half because the base is not S over 2, the base is S. So you have an
Oh,
extra half there. That
that's
will
true.
save you from a radical, but keep going.
Okay, thank you there. Yeah, because this entire base is S. So I could have also said the area of this triangle is that, but then I have to multiply by 2. Okay, nice. So this is S over 2 times S over 2 is 25. Great. So then it does save me from a radical. I have S over 2 squared is 25, but I can take the square root. So S over 2 is equal to 5. And that means S is 10. Okay, that's pretty nice. So my side length here is 10. These are all 10s. And now I have to find the side length of the bigger square, right? And I think this becomes a kind of another trigonometry-ish question. I guess we probably don't know trigonometry yet, but okay. So this is some angle chasing, I guess. There's a 90-degree angle inside there. These are 60 and 60, but the whole thing in this big circle has to be 360. So I can do 360 minus the 260s, so minus 120 minus 90. And this should give me 150. Yes. Okay. So this thing in here is 150. And so I guess similar things would tell me that these two things are 15.
But
Now, maybe
150 is
there's,
disgusting.
that's true. Yeah. So maybe there's a cleverer thing. Cleverer thing.
Luke, do you see something?
yeah.
I see Luke
So
drew a thing. Luke drew a thing.
yeah, one thing I think you can do in this is because there's that weird unshaded square in the middle, you can use that because you actually know that the side length of that square is also going to be 10. So you know that the side length of that square is 10, and that means that we can find this diagonal right here through the middle of the square. So if we do that, then we have three portions of this diagonal. One is the height of that equilateral triangle, and then there's another height of that equilateral triangle, and then there's the side length of that square in the middle. So the side length of that square in the middle is 10 plus these heights, as we found earlier, are s square root of 3 over 2 or 5 root of 3. So 5 root 3, and then there's two of them, so we multiply by 2, and then that diagonal is going to be equal to 10 plus 10 square root of 3. All right, Eli, do you want to take it from here?
Yeah, this is great. So now we have 10 plus 10 root 3 as this big thing. If I call this side length L, these two things are L, then, well, okay, what's the diagonal of a square? It's just L times root 2, right? Pythagorean theorem, L squared plus L squared, square rooted. And so L root 2 is here. Divide by root 2 and I get L. But we actually want the total unshaded area. So I actually don't care about dividing. I'm just going to square both sides. And I get, let's see, 100 times whatever 1 plus root 3 squared is, which is 4 plus 2 root 3, because you get the 1 and the 3 and the 2 times the 1 times the root 3. Yeah, okay, that looks good. That's equal to L squared times 2. And so I can just cancel out the 2, make this, I guess, 2 plus root 3. And that's what L squared is. We want the total unshaded area inside ABCD. So if we have the big ABCD, we know that the area of this whole thing, which is L squared, is 100 times 2 plus root 3. And we have to get rid of what we're given as the shaded area of 100 root 3. So if we take 100 times 2 plus root 3 minus 100 root 3, I see something really cool happening. The 100 here times the root 3 just totally gets canceled out. And we're left with just 100 times 2, which is 200. That's nice. It feels like the kind of answer that would be correct, but is it really correct? Looks like it is.
Ooh. Wait, I want to make a comment here. So I didn't expect it to be this nice. I thought you'd get something disgusting. Can you go back to the problem statement? There's a thing when you do math counts contests. If you do enough math counts contests, you realize that they usually say things like express your answer as a common fraction whenever it's actually a fraction. And they say express your answer in simplest radical form whenever there's a radical form. The fact that this didn't say simplest radical form is actually a signal that you don't have any radicals, which I did not know this until the moment you got the answer. And I was like, whoa, now you know you got the right answer.
So if I ever see that, I should just guess like 300, just guess a nice
Oh,
number.
yeah. Awesome. We got two more questions that I wonder if we can do them. Let's keep going. It's Luke.
Alrighty, question number 29. The second to last question here, and it reads, a positive digit a digit in a positive integer is dominant if at least half of the digits in the integer are the digit d. How many positive integers less than or equal to 2026 have at least one dominant digit? Okay, so this is quite a difficult problem that we are trying to solve right here. And let's do some casework. So we could have single digits with one. Okay, let's not write single. Let's just say we have one digit numbers, or like one through 9, those numbers. 1 digits, 2 digit, 3 digit, or 4 digit. And 4 digit is not going to be all of the 4 digit numbers. It's just going to be 1000 to 2026. So the reason why I'm doing this like this is because in 1 digit and 2 digit, we have different cases than we have in 3 digit. In 3 digit, we need at least 2 digits of a certain type. In 2 digit or 1 digit, we're actually automatically already having a dominant number. Think about a random number. Let's just say 68, okay? 68, both 6 and 8 are already dominant digits because half of the digits in the integer are 6, half of the digits in the integer are 8. So all of the numbers from 1 to 99 are dominant, so our first two cases are taken care of. All right. So now we know that we have those 99 numbers, and we'll move on to 3-digit numbers. Every number from 100 to 999. Okay, so instead of thinking about them in this numerical order, let's say that we have 9 options for our number that we want to be dominant. Actually, well, we have 9 options for the digits 1 through 9, and then we have 1 option for the digit 0. So these are our 2 different cases that we're going to be doing here. The digit 0, we separate it because we can't have that first digit be 0, so it's going to be a little different. So every 3-digit number that has 0 as the dominant digit. Also notice, backtracking a little bit, you can only have 1 dominant digit in a 3-digit number because you have 3 digits, which is an odd one. So you need 2 copies of that digit in order for it to be dominant. So 2 is going to be the max that you can have.
Ooh, I have a suggestion. So I don't know how to do the whole problem yet, by the way. I'm just like backseat watching this thing. But you see, the issue is that you also could have three of them. And so whenever I see a thing where it's like, oh no, is it two or is it three? I start thinking complementary counting. For the three-digit ones, if there's no dominant digit, what does that mean about the three digits?
Ooh, yes, you're right.
I,
Okay.
I can't do the four-digit yet. I'm just like backseat watching, but I think I can do the three-digit one nicely.
Yeah. So yeah, that is a good way to do 3 digits. If you have 3 digits, that means that all of the digits have to be distinct if it's not dominant. So we're going to do that complementary counting thing, count the things that we don't want like we did earlier. So if we have all of the digits as unique, then we have 9 options for that first digit. And then for the next digit, we can choose any of the digits 0 through 9 except for the one that we chose for this number right here. So we have 9 options for that, and then 8 options any of the 10 digits except for the first 2 that we chose. So 9 times 9 times 8 is going to be equal to 792. And these are the amount of 3-digit integers that are not dominant. So
Ooh, I want to
900.
jump in. I want to jump in. This is right, but I think there might be people in the audience who are like, how did you get that? Like, why isn't it 10 times 9 times 8? Or why isn't it 9 times 8 times 7? Like, there was something really sneaky you did there, which is really clever. Could you
Yeah.
just like explain a little bit slower?
Yeah. I wanted to get through it fast because I was like, oh, Professor
Yeah,
Loh. All
understand.
right. So there's 9 options for our hundreds digit. So we have 3 digits right here, hundreds, tens, and ones. So there's 9 options for our hundreds digit because we can choose any of the numbers from 1 through 9, and we can't choose 0, right? So let's just say that we chose the digit 4, for example. Then for our next digit, we can choose any of the digits from 0 through 9. But if we want it to not be dominant, then we can't choose the digit 4 because we can't have 2 copies of a 4. So we have 9 choices now for our next digit. So 9 for our first one, 9 for our second one, because we can choose anything but this 4. And let's just say we chose a 0 here. So now for our last digit, we can choose any of the digits 0 through 9 except for 4 or 0. But that's just an example. But in every case, we're going to have 8 options for our last digit. So 9 times 9 times 8 is going to be equal to 792. Then there's 900 total numbers from 100 to 999. So 900 minus 7092 equals 108 total numbers, 3-digit numbers that are going to be dominant, and then 99 for these 1 and 2 cases. All right. Okay, so now we have the most difficult case of all, which is going to be this one right here. 2026. Okay, wait, no. Any of the 4-digit numbers up to 2026. So that's going to be 1,000 up to 2026. All right, so what's really interesting about this is that the vast majority of these numbers are going to start with the number 1. So let's split it up into 2 different options. We either have 1000 to 1999 or 2000 to 2026. So these are 2 different things that could possibly happen. Now, if we have a 1,000, one of the numbers from 1,000 to 1,999, most likely what we're going to have as our dominant digit is going to be a 1. And what I mean by that is that the ones are different from all of the other digits. Professor Loh, did you have something you wanted to say?
I'm again, because it's easier for me because I'm not talking, but I'm just like, I wonder if we can think about complementary again. Whenever it looks messy, I'm like, what are the other ones? And I could
Yeah.
be wrong because I haven't thought everything through yet. So what do you guys think?
Yes, I think that is also a good idea here, but I think it's a little different than when we had it previously because we have to think about the 1 now instead of just thinking about other things.
That's right. So you'll probably also have to deal with the one and the two, but I'm wondering, like in general, like four-digit numbers which have no dominant digits, there might be a nice way to say something about them.
Yeah.
Because I think they're still all four digits different.
Yeah, because you can't
Because
have
once you
two
get
that are
two,
the same. Yeah, exactly. I mean, if
yeah,
you have two that are the same, then that's automatically at least half because half of four is two. So you can still do the thing with the other, all of them being different. I was just gonna, if because I thought you were dealing with the case of with one at the beginning, I was just gonna try to solve the one with two because
yeah.
it's
I think
just
this
like
is good
listing.
teamwork.
Yeah.
I think
Yeah.
it's good teamwork because you see, I think you do have to do something special with the one starting with the one, but I think conceptually it'll be easier to think of it as I need four different digits. And then so like there's the problem with the one starting with the one, and then Eli has just managed to bash up the, the 2000s ones.
Yeah. Yeah. So if we had like all the 4-digit numbers, it'd be pretty easy to see we just need 4 different digits in order to make it not dominant. But unfortunately, we don't have all of those numbers, so we have to do something a little bit different here. So we have to do 1,000 to 1,999. And we have to keep very careful track of this 1 right here. So if we want our number to be not dominant, because it's easier to count the things that we don't want instead of the things that we want, if we want to count the number of ways to make a number not dominant, then we have one option for our first digit, right? Because it has to be 1, right? All right, so then for our next digit, we're going to have 9 options. We can choose any digit except for the digit 1. So we're going to have 9 options here. And then we're going to have 8 options for the next one. Let's say we chose the digit 8 here. We can choose any digit in this next one except for 1 or 8. So we have 8 options here. And then finally for this last digit, we're going to have 7 options because we can choose anything except for any of the ones that we chose for these first 3 digits. So 9 times 8 times 7 is going to be equal to 504. So 504 is the total number of integers that are not dominant from 1,000 to 1,999. And there are 1,000 of these integers. So 1,000 minus 504 is going to be equal to 496 integers that are dominant. And then we have to add this to the number of integers between 2,000 and 2,026 that are dominant. And Eli says there are 20. So 20 integers here that are dominant for a total of 516 in the 4-digit case. 516 in 4-digit, 108 in 3-digit, and 99 in 1 and 2-digit. Adding all of these together, we are going to get 723, I think. All right.
Looks right to me. Okay. Let's see if
Now
723
the
is our
moment of
answer.
truth. Oh no.
No, not even close. Wow, that's crazy. Okay.
Oh no! Okay, so I don't know either. What's going on? What's going on? Let's try to figure out. Hey, chat. Hopefully you guys are all here too. So, what's going on? Where did we screw up? Because by the way, I haven't done this before either. Oh, somebody has put a chat thing here. Someone says 9 times 9 times 8 is not 792.
I just messed up the math, maybe? Yeah, I just messed up the math.
All right, let's try
Okay.
it. Let's try it. Let's
I
try
just I just went with it because I didn't want to compute that. Okay.
it. Yeah, I'm the same. Okay, keep going.
All right. 9 times 9 times 8 is actually 648. I'm sure somebody was saying this and I wasn't paying attention when I multiplied it out. Then this is going to be 648, and this is 252. All right. Now adding up all of these again, we are going to get 863. Wait, no, 67. 867. All right, 867 is going to be your final answer. This is why you write things out and multiply them nicely and normally and not just do everything in your head. And 867 is
Yay! Okay, and by the way, I want to emphasize, I actually didn't check the arithmetic either, because as far as I was concerned, the most interesting part of this question is like, why is it true, and what do you calculate? We got one more question to go. We're going to go a little bit over time. Let's see if we can do this question. Unfortunately, Eli got the failed to load message. So, but that's okay, because this is a group work, right? So let's see. Luke, why don't you start kicking us off? I'm going to make Luke's thing big first so everyone can read the question, and then we'll add more people on, especially as Eli's thing works. Oh, Eli's thing worked already, but I'll make Luke's thing big first.
Okay. We have a very interesting equation here that looks quite annoying, I'd say.
What?
The square root of x squared plus square root of x plus square root of, I'm just going to write it again just so I can like process the information, you know? It says express your answer in a radical form, so we can't just guess integers until we get the right answer. That will not work here. So we're going to have to think of something more interesting. And the first thing I see is that we have x squared plus square root of x and x squared minus square root of x. So something that really nice that will happen is if we multiply both of these square roots by each other because of the difference of squares, we'll get rid of this inside square root. So we want to find some number of ways to multiply them by each other. And if we square this entire side over here, we will get a way to get rid of some of these outer square roots and some of the inner square roots. So that seems like a good idea. So squaring this entire thing, we get x squared plus square root of x plus x squared minus square root of x, just putting those terms first, plus 2 square root of x squared minus square root of x times x squared plus square root of x. If you multiply this out, it's equal to x to the fourth minus x because of the difference of squares. So plus 2 squared of x to the fourth minus x is going to be equal to 4. Okay, this cancels out with this, which is really, really nice. So 2x squared plus 2 square root of x to the fourth minus x is equal to 4, or x squared plus square root of x to the fourth minus x is equal to 2. Okay, so now what we want to get rid of is, what we want to get rid of is this thing right here, this square root. It's annoying right now. And a way that we could do that is we could subtract x squared from both sides of the equation and then square it. The only problem is we're going to get a very... No, we're going to do it anyways. We're going to do that. Okay. Oh, no, no one saw that. Okay, we need to add another thing. Right now we are at the equation x squared is equal to 2, I believe. So the square root of x to the fourth minus x is equal to 2 minus x squared. Squaring both sides, we get x to the fourth minus x is equal to 4 minus 2x squared plus x to the fourth. And yes, it actually happens very nicely. The x to the fourths cross out. So now we're left with a quadratic equation, and we know how to solve quadratic equations. So this is going to be very, hopefully not too difficult. 2x squared minus x minus 4 is equal to 0. I did this by adding 2x squared to both sides of the equation and subtracting 4 from both sides of the equation. Quadratic formula time, x is equal to 1, negative 1, so negative times negative 1, plus or minus the square root of 1, negative 1 squared, minus 4ac, which is going to be 4 times negative 4 times 2. Wait a second. Yes, 4 times negative 4 times 2. So that's actually going to be plus 32, I believe. And then divide all of this by 2. Oh, 4 actually. Okay, so x is going to be equal to 1 plus... okay, now let's go back to our original equation and see what they're asking for. What is the value of 8x? Express your answer in simplest radical form. So 8x is going to be... Oh, wait, I see something I did wrong, and now I have to fix it. I thought something was wrong. Something was up. So over here, actually, I messed up. It's not 2x squared. It's going to be 4x squared. Just a multiplication error. So then going over here, this is also not going to be 2x squared. It's going to be 4x squared. And then this over here is going to be 4 times a times c is going to be negative 64, not regular 64. So plus 64 is what we're going to have. And then this bottom is going to be 8, not the regular 4. So our final answer is 8x. So 8x is either going to be 1 plus or minus square root of 65. And we need to decide now between 1 plus square root of 65 as our answer and 1 minus square root of 65 as our answer. So there should be something in the problem that tells us which is going to be the answer.
Yeah, I think that I can actually answer, even though my screen has been going haywire. It's that you're taking the square root of x at some point, and if you take the square root of a negative number, that's going to be sad. So I think we should go with the positive one, because 1 minus root 65 would be sad if you take the square root. So let's go with the positive one. Yeah, because it said real number x. I don't know. Would it actually work like with the complex stuff if you plugged in the negative value?
Ooh, the complex stuff, the only reason it'll get messy is because many people are used to things like square root of minus 65. You're like, okay, that's so square root of minus 64. That's like 8i. Except then the weird thing is, what if you took the square root of I? You see, the problem is that, actually the real problem is that whenever we write the square root sign, if it happens to be a real number, if it's a square root of a non-negative integer, we're always like, it's the positive square root. You might remember that, because when I was learning algebra, I was always like, why don't we say square root of 64 is minus 8? Actually, it's a notation thing. We've somehow declared the square root sign is called the positive branch of the square root. Now, the issue once you have i's is because there's no such thing as which of the i's is more positive than the other. 1 minus 2i more positive or less positive than minus 1 plus 2i is actually weird. So the main problem is that we don't have a good definition for square root symbol with like an I inside it. So that's, I think, the easiest explanation. But I just popped online on the screen because I wanted to show my emotion for the reveal because I don't know what the answer is. We don't know if it's right. So,
All right,
did we get it?
1 plus square root of 65. Yay!
Yay! We did it! Okay. Well, with that, unfortunately, that brings our live solve to an end. Happy Pi Day to everybody. It's actually still, oh no, it's not Pi Day for me anymore because I'm in England. It's apparently 1:09 a.m. But
Oh
it's
my word.
okay. Oh no, but it's still good for you guys. I hope that you guys had as much fun as we did. Every time I feel like I wish I could draw like this stuff too, but I'm always traveling, so I don't get to draw. But it's a huge pleasure to work with them. For me, sometimes I saw somebody sent me a message being like, "Hey, it looks like you're doing the heavy lifting." That's not true. It's just that it's easier to be the backseat driver. So when somebody is watching as it's going, I get to notice things. I also will say I definitely got to see some really interesting ways of solving problems today, and that's actually why our style of teaching is we always want to have two people who are both really clever, showing you how they think. Because ultimately, the most important thing is not to get just the right answer. In fact, sometimes we got the wrong answer. But the thought processes and the logic are really, really interesting. If you liked learning this stuff this way, stay subscribed to our stuff. We actually do live solves quite regularly. And whenever we choose to work with a competition like MathCounts, it's because we hold them in very, very high regard. I also want to endorse and say, anyone who's in middle school in the United States, please make sure your school registers for MathCounts. It is a great opportunity, and it'll even help all of the other people who go to your school too. Because unlike the other math contests, you need a team. And the team is what gets all these people involved in the school, not just you who's watching this. All right? It also gives you friends. I made a lot of friends through MathCounts. So, and I guess actually, even if you're homeschooled, right? Even if you're homeschooled, you get to play this. Luke, is that what you did?
Yes, I did do math counts even though I was homeschooled. It's pretty great.
Yeah, it's great. Okay, strong endorsement. But with that, we unfortunately have finished up for the night. So nice to talk to you all.